In this video, we're going to be talking about a paper, IX, a Protected Data Plane Operating System for High Throughput and Low Latency by Belay from 2014. To begin with, what we're going to talk about is OS network performance. And then we're going to look at IX as a case study of that network performance. Okay, so let's look at, describe a high-performance network server. So for example, let's look at memcached. Memcached is this in-memory key value storage server. So it's often used as a front end for another website. So basically it will cache responses from websites, the most recently used elements. Some aspects about it are there are often very high request rates. And we have short requests and responses. Okay, so this is, for example, memcached, which is an in-memory key value store. What else do we have? There's lots of clients. So it's not as if there's just one client talking to the server, which would limit the amount of parallelism. There's lots of different clients coming in, which allows for a lot of potential parallelism. And the reason for that is because these are all distinct from one another. What we'd like is if there's high load, we want a high throughput. So we want to be satisfying lots of requests per second. So that's what we would in fact be measuring. We want that to be big. When there's low load, then our goal is to have low latency. Okay? That is, we're trying to increase, so big requests per second, and here we want to decrease seconds per request. Or let's make it better. Let's look at something like milliseconds per request. And we also want a low tail of latency distribution. So for example, let's say this is our distribution of latencies. One possibility might be we had, let's say, a distribution that, I don't know, looked like this. Okay, so here's the 50th percentile. Here's, let's say, the 95th percentile. An alternate distribution might be something like this, where our 50th distribution is not far, but our 95th distribution is way over here. So we are trying to not have these high tail latencies. We want low tail latency. And these are some of the goals of many web servers. But in this particular case, we are going to take advantage of the fact that we're completely in memory. So we don't have any disk I/O and so on. That's going to increase these latencies. What are the hardware limits that we're looking at in order to satisfy this? Well, let's look. So if we look at the hardware, because we're certainly limited by our hardware. And we're kind of looking at how well can the operating system take advantage of the hardware. So if we look at 10 gigabit Ethernet, this would allow us to have maybe 15 million tiny packets per second. If we went up to 40 gig Ethernet, that would increase us to 60 million tiny packets per second. And sometimes this 40 gigabyte is just 4 bonded 10 gigabytes together. For RAM, just dealing with RAM, we can get a few gigabytes per second. Interrupts, we can do about 1 million a second. Contended locks, that is locks that other cores or threads are waiting on, we can do about 1 million per second. Intercore data movement, so that's kind of copying data between different cores. And this is a few million per second. What else do we have? So what does this tell us? This tells us a couple of things. Our basic limitation is if we're limited by Ethernet and RAM, we can get kind of 2 digits, millions per second. I remember when I used to work at Google, we'd often have TGIFs, and they talk about various either goals or achievements that had happened in terms of growth that had happened, and they never wanted to be too specific because they were talking to the whole company, and so there were potential leaks, but they talk about it to a decimal place, basically. So this would tell us that there are, between 10 and 99 million per second. If, however, we're limited by interrupts, locks, and etc., then our limit is lower. We're in the single-digit millions per second, maybe only 1 million per second. Let's actually think about this a second. If we only get 1 million interrupts per second, does that mean we're limited to 1 million packets per second? No, because we can actually handle multiple packets per interrupt. So an interrupt may tell us about multiple packets that have come in. But still, interrupts, continued lock, intercore data movement, all are really going to hinder the underlying hardware capacity, which can be really, 15 to 60 packets per second, depending on the exact Ethernet we're using. As far as latency, that can be really important. So latency is important, especially if we look at, let's say, a web page. We often are making certainly tens and often hundreds of requests to servers for, let's say, a jQuery script, for fonts, for the JavaScript, for for various tracking sites, for images, for HTML pages, all that sort of stuff. So if you can imagine hundreds of items, if your 99th percentile latency is slow, on average you're going to hit 1 or 2 of those in a particular loading of page. And if your page doesn't load until all of it's there, that means you're limited by your tail latency. So latency really, really matters. There are a sum of different things that can cause latency. So we have, let's say, the network. So these are sources of latency. Okay, so the network, we run into things like, let's say, speed of light, switches, things like that. Speed of light, if we look, for instance, at a light year, what's that a measure of? It's a measure, of course, of distance. I think a lot of people somehow think it's a measure of time, but of course it's a measure of distance, the amount of the distance that light will travel in a year. One question is, how long is a light nanosecond? That is, how far can light travel in a nanosecond? And the answer is about a foot. So when you're talking about billions of things per second, then you're really talking about feet matter. So that's why, for example, high-speed traders are so interested in having low latency connections to the exchanges, that they are willing to, for instance, reroute fiber so that it doesn't go around a town but through a town, because we can be getting rid of, if we can get rid of 1,000 feet, right, then that is going to reduce the time by a microsecond. All right, so that's one source of latency. A second source of latency is interrupts. For an example, if you've got an Ethernet driver, you program the Ethernet driver to generate an interrupt when the receive buffer is some percentage of full. So if you imagine you program it so that it will generate an interrupt when it's half full, that means you have some latency for those first packets that come into the buffer, waiting for enough packets to come in until half the buffer's full, and then the CPU will be notified. We have queue operations. Right, we can imagine often when an interrupt will happen, let's say for a Ethernet driver, Ethernet card, the data is copied into some queue in memory to be dealt with. Similarly, when something is sent, when an application does a write to a socket, that data actually doesn't get sent immediately. It gets copied to be sent later. We have sleep and wake up issues, right? If we look, for instance, at our latency for receiving a request and returning a response, if our application isn't actually running at that time, we've got to wake up that application, sleep the previous application, wake up a new application. We've got the cost of system calls. We have the cost of intercore data movement. If we're have multiple cores that are actually ending up dealing with the request response cycle. And then we also have random fetches. So our goal in order to increase latency is to remove as many of these that we can from the equation. So we're going to look at removing interrupts. We're not going to do any queuing. We're going to actually have one process running on a core. So we won't have sleep and wake up issues. We're not going to move things between cores. We do have to worry about system calls, but we're going to try and amortize the cost of system calls by using batching. And so these will have the effect of reducing latency. So we're going to actually be increasing our throughput and reducing latency. That's our goal, so which is not a bad trade-off. We'll see that there is some trade-off to be made, so some cost we have in doing this. This is going to be the low load case. So let's look at sources of latency in a high load situation. In a high load situation, it's almost always determined by queuing. So efficiency, that is a high throughput, actually reduces the queuing time. So that helps. One problem that can happen is if you have bursty arrivals, right? So if you have a incoming traffic that looks like this, it is easier to have low queue times. On the other hand, if your traffic is more bursty, so it's sometimes like this, but occasionally spikes, then you often can get queues at these bursty times. And what those do is increase, of course, the queue time. The other thing to look at is if you have service times that are bursty. So usually it takes so much time to actually satisfy a request, but sometimes it takes a lot longer. That also can increase the queue times. Structural problems can do that. For instance, if you have load imbalancing. So if you've got one server that has a lot of requests and another that are very few, that can cause queue time. Or if you just got nobody that's actually servicing a queue for some reason, that's a problem. So latency is hard to reason about, and it's also hard to fix. One thing that often happens with queues, if you just imagine you've got different kind of points along the system that you're handling. So we have a packet coming in here, and here we have the app dealing with it, and then returning the packet in some way through a set of queues. What can often happen is you're limited, of course, by your weakest link. But what often happens is, let's say that this guy is fairly slow. You're going to get a large queue built up behind him, and that's going to really increase your latency for everything. It turns out for Ethernet, maybe what would be better to do is say if we're going to have a large queue here, maybe it's better to stop accepting these packets. We'll talk a little bit more about that a little bit later.